Hello everyone. Today we'll be solving the problem number 133, clone graph. So what the question states here, we are given a reference to a node. So we are given a reference to a node. You can clearly see here, we are given a reference to the node in a connected undirected graph. So this undirected graph, and they have mentioned connected undirected graph. And we have been given a reference to individual node. So that's what they have given. Each node contains a val. Val means value integer representing the node's value, and a neighbors list containing references to the adjacent nodes. So one thing is each node consists of the value, and neighbors list means containing references to the adjacent nodes. So these two things we have to keep in mind. One thing is every node has a value, and neighbors list. Also, every node has neighbors list, nothing but containing references to the adjacent nodes. So that's what they have given here. So what is our main task? Our main task is to return a deep copy clone of the entire graph. So we have to return a deep copy of the entire graph. So what does deep copy mean here? Each node in the original graph has a corresponding node to the clone graph. The structure or the edge of the graph remains same. So that's what that's what we need to do. We have to return a deep copy clone of the entire graph. So I'll just show this one. They have clearly mentioned in the diagram actually. See here, they have given the conditions here. Just give me a second here. Yeah, here let's consider this example, first example that they have given here. So 1, 2, 3, 4. So these are the nodes, right? So 1, 2, 3 and 4. These are the nodes. Value we are having 1, 2, 3 and 4. And these are the edges, right? So first diagram you can clearly see here, you can't return the same graph they are saying. So we shouldn't return the same graph. This is first condition we need to keep in mind. And second thing, this looks like a new clone. The nodes are new and graph looks the same. Here nodes are completely new. That's what so this is the requirement or the condition for the deep copy they have given here. See, so here we are having new nodes, nothing but 1, 2, 3, 4 are completely new. So this looks completely new, and graph looks the same here. 1, 2, 3, 4, 1, 2, 3, 4. This is completely identical and the nodes are completely same. So this will be the output. This is what we have to do, right? So just give me a second here. So I'll just come, just give me a second here. The third condition is the second condition. This matches actually, this is fine. And the third one they have given here is the nodes were cloned here. So see here, the nodes were cloned, but the graph is messed up. Why the graph is messed up here? See, so we are having the value 1 here. Here also we are having the value 1. Here we have the value 2, but we are having the value 3 over here. So the value differs here, right? The value of the nodes are present actually 1, 2, 3 and 4. I mean all the nodes are present, but the graph is messed up, doesn't have the same connection. So from 1 we should have the connections to 2 and 4. Here from 1 we have the connections to 3 and 4 instead of 2 and 4. So they are saying this is messed up, so we shouldn't consider this one. I mean this one. So the two conditions we need to consider here is, one thing is we shouldn't return the same graph, right? That is one thing. And the second condition here is it shouldn't have, nodes should not have the, nodes should have the same connections. If nodes doesn't have the same connections, that should not be considered. These two conditions we need to consider. I hope this is completely clear. So and the example, let's come to the example one. They have mentioned the adjacency list here. You can clearly see for this one. So let's consider this one here. 2, 4. Adjacency list means here this one. Just give me a second here. So from node 1, where the edge is moving, that we will consider the adjacency list. So for 1, here this one, right? Here it is moving to 2 and 4. So adjacency list will be for node 1 will be 2, 4. Same goes with 2 here. For 2 it is 3 and 1, right? Or 1 and 3 here for 2. So 1 and 3 they have considered. For 3 it is again for 3 it is 2 and 4. So that's what they have considered here, right? So the final one is 1, 3, nothing but for the 4. For 4 it is 1 and 4. So adjacency list they have mentioned here, and output has to be same, as we are just cloning the graph according to the conditions or the requirements they have given. In explanation also they have clearly given here. You can just go through the explanation as well, just to understand that one clearly, right? So I hope this is clear. And the second example, they have just given one node here, and we have got the empty array here. Why? Because we don't have the neighboring node at all to consider the edges or the adjacency list. So the output will be empty array. So they have given in the explanation, note that the input contains only empty list. The graph consists of only one node with a value 1. So we have the value 1 here. You can clearly see, right? The node value, and it does not have any neighbors. That's what I said. If we are not having any neighbors, so there will be no edges at all. So the output that we got here is array, empty array, right? So this is fine. I hope the question is completely clear. Let's discuss the approach first. I'll just consider the same example. Example 1 they have given here, right? So I'll just consider this one example for the approach. And after discussing the approach, let's discuss the edge cases one by one. Then finally write the code and discuss the complexities of the code that we have written. Initially, as usual, let's discuss the approach. So here I have considered the same example that they have given in the example, right? So first thing we have to keep in mind here is we are going with the DFS. So DFS or the recursive DFS to solve this particular problem. So they have mentioned the adjacency list here. We saw this one adjacency list, what's adjacency list? The output has to be same, right? So first thing what we will do here is we will start from node 1. We'll be making use of the DFS. So first step, so I'll just give here step 1. First thing is we will start from node 1. Let me give here start from node 1. We are starting from the node 1. What we will do? We will clone node 1 and store it in the hash map. So we are dealing with this one, node 1. We will clone node 1 and store it in the hash map. Hash map contains key and value pair, right? So here hash map, now it will be 1 and it will be cloned of 1, right? So we are cloning node 1 and storing it in the hash map. That's what we are doing it. So hash map, this looks like this. So now we will visit its neighbor nothing but 2, 4 adjacency list. So here for 1 we have the neighbors 2 and 4, right? That's what we will be visiting. So I hope this is clear. This is for the step 1. So now we got 2, 4 here. This is fine. So let's move on with the step 2 here. Step 2, what we'll do? We will move to node 2 now. They have started from node 1. We'll move to node 2 here. When we move to node 2 here, first what we are doing? We are cloning node 2. Now we are considering node 2 here, this one. We are cloning node 2. So it will be now in the hash map 2 we are considering, and this one will be cloned of 2, node 2. This is fine. This looks like this. So next we will visit its neighbor. For the 2 neighbors are nothing but, again it's same, 1 and this one is same, and 3. 1 and 3 for 2, right? So it will be, we are visiting 1, 3 here. This is fine. So since 1 is already cloned, we have already cloned 1, you can clearly see in the step 1. Since 1 is already cloned, we will connect clone 2 to clone 1. So we are connecting here clone 2 to this one, clone 1. So next we will move to node 3. So the output will be here, this one. We are connecting clone 2 to clone 1. Why we are doing that one? Because 1 is already cloned. We know that one, right? That is the reason we are connecting clone 2 to clone 1. So this one next we will move to node 3. So I'll just come here. Let's give it as this one, step 3. We have to move to node 3 here in this case, right? So we are just moving to node 3. First we will clone node 3. So node 3, it looks like this, right? And the hash map 3 cloned of This is fine. So we are just cloning the node 3. So next we have to visit its neighbors. So here let me come here. We are considering 3. We have cloned 3 now. We have to visit its neighbor. One is 2 and one is 4. Right? 2 and 4. So I'll just come here. We are visiting for 2 comma 4 here. This is fine. We have just visited its neighbors. Since we know that 2 is already cloned here. In this case, 2 is already cloned. We have to connect clone 3 to clone 2. It's already connected. So clone. So sorry, just give me a second here. Yeah. Since 2 is already cloned, we are connecting clone 3 to clone 2. I hope this is clear, right? So the next step is we will move to node 4. This is the final step here. Move to node 4. This will be the output here. In this case, we are moving to node 4. Here, what we will do first, so I'll just come here. Now we are considering this one, 4th node. So let me come here. What we will do here, first we will clone 4. This will be in the hash map 4 cloned of 4. This is fine. Next step is we have to visit its neighbors. Let me come here quickly. Visit its neighbor means 1 is 1 and 3 are the neighbors of 4. Edges we are considering, right? We are just visiting the neighbors. So this will be 1 and 3. Sorry, not 1 and 4. We are considering 4 itself, right? The neighbors will be 1 and 3 here in this case. Since we know that 1 and 3 both are already cloned, right? We will connect. Now what we will do, we will connect cloned of 4 to this one, cloned of 1, and also cloned of 3 to clone of 1. So these two steps we need to keep in mind. Cloned of 4 to cloned of 1 and cloned of 4 to cloned of 3. So sorry, this one, did I miss something here? 4 to clone of 1 and also this one I missed here completely. So yeah, this one has to be 4 we are considering here, right? So this one has to be 4 cloned of 4 to cloned of 3 here. Sorry, this I got confused here. So 1 and 3 are already cloned. So we are connecting clone 4 to clone 1 here, this one, and clone 4 to clone 3. So I hope this is completely clear. This is step 4. So finally, what we will do in the step 5, we will just backtrack and complete cloning for all the nodes. So final final output will be, so here we will just backtrack and compute cloning for the all nodes. So final clone graph that we got here is, so let's consider, let me come here, the same thing, right? 2 comma 4, 1 comma 3, 2 comma 4, 1 comma 3. That's what we got here. 4, 1 comma 3, 2 comma 4 and 1 comma 3 here, which is same as the output that they have given. So here for 1 comma 3, 2 comma 4, you can clearly see here, right? This part. So it is same as the output. So recursive DFS, this approach works absolutely fine. So this is the approach that we will go with, right? So I hope this is completely clear. Now let's discuss the edge cases one by one. So the first edge case I'll be going with here is single node with no neighbors. So the same as they have given in the example 2, I think, second example. So this will be, input will be this one. We have only one node here. So with the value 1, we do not have any neighbors at all. This is graph basically. We have only one node and we do not have any neighbors at all. So here input will be this one and output will be the same empty array, because we don't have edges at all, right? So graph contains only one node with no edges, because so the output will be this one. So second edge case will be empty graph. So let me consider here empty graph. So graph is completely empty here. I'll just give here empty in this case for the graph. So output here, input will be this one. Output will be same for the empty graph. This is fine, right? So this is the output for this one, empty graph. So because no nodes exist in the graph at all, the output will be empty array here. In this case, I hope this is clear and this is clear. These are the two edge cases that we need to consider. I hope all the edge cases are clear. I mean, two edge cases are clear. Next, let's start writing the code. So let's start writing the code. So we considered the edge case where if input graph is empty, then we have to return null, right? So I'll just write the simple if condition here. Node equals null, or if not of node also you can give anything. Both works, right? If node equals null, I'll just return null in this case, or I'll do one thing. Let me write this one here itself. Return null. This is fine. The next step is we are making use of the map to store the cloned nodes. That one we saw. We made use of the hash map, right? To store the cloned nodes. So I give here let map equals new map. This is fine. We are just making use of the hash map to store the clone nodes. Now we will make use of the recursive function to clone the graph. We'll be making use of the helper function or the recursive function to clone the graph. I'll just give here const. Let me give the name clone itself for the function. This one will be root. This is fine. If the node is not cloned yet, so we have to consider that value of the node, right? So how can I write that? If simple map dot has root dot value. This is fine. If the node is not cloned at this one, if the node is not cloned, then what we will do further, we will clone that node. How? I'll just make use of the set property, and I'll just give here root dot val, and I can just consider new node here, new node of root dot value. Same thing. We are cloning that node here. And this step, if condition, if the node is not cloned yet, then in the 8th line, what we are doing here, we are cloning the node, right? That's what we are doing. I hope this is completely clear. We already saw the approach and example that we considered, right? I hope this is clear. Next line is we will recursively clone the neighboring nodes as well here. We will recursively clone the neighbors as well. So I'll just make use of get here. Let's just make use of a get property, the hash map. I'll just give here. We are recursively cloning the neighbors, right? I'll just consider here neighbors equals root neighbors dot map clone. Let's pass the clone here. This is fine. So the next step here is we have to return all the cloned nodes, right? So let's return here. To get the value of I'll be making use of the get property of the hash map. So I'll just give here root dot value. In this case, we are just returning the return. We have to return all the clone nodes. That's what we are doing here in the line number 11. Sorry. Yeah. The last one, the last step is we have to start cloning from the given node, right? So I'll just return in this case clone of node. This is fine. This is it. So let me format the code once and let me hit the run button. So here, look, I have given. Sorry, this is null actually. It's fine. I didn't see that one at all. Yeah, this is fine. Yeah, now you can clearly see the sample test cases are getting passed here. So let me hit the submit button. So you can clearly see here all the test cases are getting passed. So the code works absolutely correct in this case, right? So what will be the so let's quickly discuss the time complexity and the space complexity of the code that we have written. So the approach that we went with here is DFS, or the recursive DFS, you can call this one. Yeah, with hash map, right? Recursive DFS with hash map. This is fine. So here in this case, what will be the time complexity? The time complexity will be, sorry, just give me a second here. The overall time complexity would be big O of n plus e. What is n and what is e here? The overall time complexity would be big O of n plus e, where n is nothing but nodes, the number of nodes, right? And e is nothing but the edges. So each node and edge is processed exactly once. That we know. We saw the same thing in the example and approach, right? So each node and edge is processed once, and overall time complexity would be big O of n plus e, where n is nothing but nodes and e is nothing but edges. So I hope this is completely clear. So what will be the overall space complexity here? Space complexity would be big O of n as well. Why it is big O of n? Because we are making use of hash map. One thing we know, that hash map stores the clone nodes, right? So we know this. Hash map stores the clone nodes, as well as we are making use of the recursion as well. So somewhere, just give me a second here. You can clearly see here one thing. We are making use of the recursive stack, right? So hash map stores the clone nodes, and also recursion stack stores big O of n calls in the worst case. So the overall space complexity would be big O of n here. So overall time complexity would be big O of n plus e, and overall space complexity would be big O of n in this case. So I hope the solution is completely clear. For now, this is it. Thanks for watching, guys.